Okay, thank you for the nice introduction, and thanks also for the opportunity to present this work. Actually, this is a work that we have been performing in the framework of a European-funded project that we call it Sincere, which is about the restoration of cultural heritage. And when you think of cultural heritage, you say, what we have to do with concrete? Well, as a matter of fact, there are a lot of concrete buildings throughout the world which are part of the cultural heritage and are part of our heritage and our conscience as communities. This work has been done with my colleague Stefania Cuenca and also with the enthusiastic work of some master students who developed their thesis with us. So as a matter of fact, let's start with the past. And we had the chance about 10 years ago to have a look to this artifact here in the island of Malta in the Mediterranean. And this was in the area of the public abattoir in Malta. You know, Malta is a tiny island in the middle of the Mediterranean, about 400,000 people living there. So it's like a city-state, and it's quite an interesting, living lab. This structure was built in the 30s. And was, as you can see, a reservoir. It served the abattoir, so they stored water there in order to clean and make the operations. It was in a severely damaged state. This is myself with my colleague, Professor Robert Borsch from Malta, and the authorities wanted to demolish it because they said, well, what we have to do, it's dangerous, we cannot trust upon. And my colleague, I have to say, was so strongly determined that he said, no, this is a part of the identity of that neighborhood. So people have always lived and grown up looking at this artifact. So we have to preserve it. And we have the chance to select this building as a pilot for a European project Resilience, in which we completely restored it, you can see, like that. And it was also an interesting educational lab. As a matter of fact, on the opposite side, one that we cannot see, the concrete was perfect, and the cores yielded 40 megapascal compressive strength, so you could say it was a very good concrete. And here, this corrosion here was the effect of the erosion of the wind-driven sand, containing also chlorides, because here you form the turbulence. The sea is here, and the main wind direction is exactly here. So this is where you have the turbulence effect due to the wind. It's not the pressure effect. Now the structure is in this shape. It's used. We used some self-filling concrete, so you can see these were some shrinkage cracks which are completely closed. It was a tough experience because, as you can see from this picture, most of the construction work went on in 2021, which was when we were having restrictions due to pandemics. Most of the work went out in summer, and in summer temperatures can be as high as 50 degrees, so we had to cast overnight. So it was a very interesting experience, and now it's fully used. And the funny thing is that the authorities realized that storing the water here, they can have during summer at an average temperature of 40 degrees. And they need 80s for hygiene issues in the area for using the water. If they store underground, the water is at 15 degrees. So they save the energy to heat up the water of the 25 degrees difference. So there is a twofold sustainability benefit. As a matter of fact, the sustainability of this restoration intervention was that we used a UHPC material, so we could make the jacketing of the columns as thin as 2 centimeters, less than 1 inch, compared to a conventional jacketing, which was done in the 70s and was a 7 centimeter, about 3 inches thick jacketing. So we reduced the material to 1/3, less than 1/3 of what it was used. So the intervention per se was sustainable because of the reduction in the volumes. But then we have the chance to work out in another project which has a broader outreach, because we also tackle with social scientists the identity value that for a community, for a neighbor, this kind of artifacts can have. By the way, now that artifact is protected by the government of Malta as a cultural heritage monument. So that was. And we said, okay, can we produce UHPC but not using, like it's done, SEM1, so having high carbon or high clinker cements? Can we try to make a UHPC-like material having the performance that we need, but using blended cement and reducing the embodied carbon. And our goal was that we wanted basically to reduce by 30% at least the embodied carbon of the material. So we started, this was the material that we used in the original project, and as you can see, you have SEM1, 600 kilos per cubic meter. We have a lot of slag. The replacement ratio, or basically the volume ratio between cement and slag is 50 by 50 in the total binder content. And we had about 120 kilos of steel fibers, which is about 1.5% by volume. We went from this and we started to say, okay, let's try to use SEM2. SEM2, according to the European classification, is a limestone blended cement, limestone filler. SEM4 is with pozzolanic cement. And we also had some, non-commercial produced LC3 with limestone calcined clay. So, sorry, there is the words are still in Italian, water and sand. You can see that the water binder ratio is 0.2 as typical. Well, the first issue that we have to solve is with these low clinker cements, how can we guarantee the workability that we need? Because if we have to make a restoration like a jacketing, we need a self-leveling, we need a self-compacting consistency. So we worked with a mixture producing company, and they gave us 2 formulations to work with. And you can see here the different attempts with limestone, with LC3 cement, with SEM2, with SEM4. Basically, we were able to keep with this SEM4 was a little bit less, but we were able to keep a good flowability, which was the starting point. But this is just the cement paste. Then you have to go with the mortar, then you have to add the fiber. So we needed this in order to get a good consistency. And we also wanted to see, okay, what are we obtaining in terms of material properties, especially, not I would say very early ages, because we did not have for this kind of intervention very intense productivity requirements, but if you make a jacketing, you want to take out the molds of the jackets quite soon. So we tested small specimens at the beginning. These are the 4 by 4 by 16 centimeter beams, and then you perform the compressive strength. And you can see that at one day, okay, with all the mixes that we tested, we were able to obtain at least 60 megapascal, which was quite a good performance for our purposes. We went up to 100 at 7 days and not more than that at 28 and still keeping monitoring. So even if technically speaking, if you look at standard, you cannot say it's truly UHPC because probably you will require higher. But anyway, it's a significantly high performance material, and for our purpose, it's okay. I tend to say, okay, this is an ultra high performance concrete for the target that we want, no matter if you don't reach higher strength, but this is what you look for. But also what was important, because we use these materials not only for compressive strength, we use for flexural toughness as well. So with the fibers, we were able to obtain a maximum flexural modulus of rupture, let's say, of about 10 megapascals. So it was a good result as well. So we ended up, then we selected the SEM4, the pozzolanic cement as a composition, and we wanted to further, dope it, mixing up some natural pozzolana, okay, just to further reduce the clinker content. So we ended up with this, and you can see here we started only with the cement, and then we added the fibers, and then we added the pozzolana, and finally we ended up in the final formulation also some phase-changing materials. Because if we want to use this as a retrofitting, not of an artifact like this, but think of a wall panel, you can also ask to your retrofitting to perform some kind of energy retrofitting task to improve, the thermal insulation, especially in hot climates. You want to keep it cool during summer and avoid to be overheated. So you can see that starting from this first target, which was what we obtained, we decreased a little bit, especially by adding the fibers, but we still had a good flowable mix. And we were able to obtain a bending performance, with the fibers, you greatly increase it, a bending performance comparable, and this was a good performance also in terms of compressive strength. We obtained what we were looking for. The flexural performance, by the way, with fibers is not only the peak strength, but we performed the test with a notch in crack mouth opening control. So you can see this is the toughness that we obtained for all the mixes that we tested. And if you compare with the plain matrix, you can see the great amount of energy dissipation capacity and toughness that we were able to obtain. We use it in this case, not steel fibers, but we use it, there are commercial ones, these amorphous alloy fibers. The good thing is that their specific gravity is more or less similar to the one of steel. So when you perform a mixed design and adjust the fresh state performance, they, the same criteria that you use for steel fibers are good as well for these amorphous alloy fibers. They come in the form of a very thin lamella, and they are not like needles. So this makes them interesting. This is a side consideration. Also, if you want to go for a 3D printing application, because they can be easily bent in the extrusion flow of the material. And this is an example, a microscope image. This is one of the phase-changing sphere. It's basically a wax-based material that was produced by a partner of the project, University of Navarra in Spain, for us. What was the other outreach? That we tested this material in different universities. Same recipe, same supplier of material, but different labs. And you can see that, for example, in Ben Gurion University, they made the same material to use with textile reinforced concrete application. They had just to adjust the water, but we got very similar performance. So this is to show up that no matter where do you produce this material, you can get similar performance. And this is also good from the point of view of sustainable UHPC application. It's not a proprietary mixed composition. It's something that you can reproduce with locally available constituents almost everywhere. Now we are in the process, because when you go with this, blended cements, we are in the process of verifying the self-filling capacity of this mix in a specific environment. This is a saline fog chamber that we have in our lab, so we wanted to test how does it behave in an environment close to the sea, so we put the specimens here, and you can see there was a crack here, and this is after 28 days, the crack here is completely healed. There are still some parts that are going to be opened, but we are keep monitoring that. The target, which was that we wanted 30% lower carbon footprint. This is simply based on the environmental product declaration of the constituent. So this is just, I would say, the preliminary step, but going from SEM 1 to SEM 4 and adjusting this, we got an improvement in terms of carbon footprint, considering the original composition and considering the new one, which is complying with our requirements. So actually, what can we conclude? Obviously, you need to work with admixtures technology developers to have the right products in order to get the fresh state performance that you want to produce the consistency of the material that you like. But we were very happy that we could demonstrate that we could produce UHPC-like materials featuring good compressive strength, but most of all featuring a very significant flexural performance and toughness performance using low clinker, low carbon binders. We demonstrated that it's feasible to have a 30% reduction of the embodied carbon footprint, and if we keep the mechanical performance, we can keep, and the durability, we can keep the same benefits coming from the UHPC technologies. Properly, I will say this is a strange sentence, because 7 days could not be really early age, but it's still something that you do not compare to the 28 or 90 days, and it's related to the productivity and are fit for the applications that we wanted. And also we are investigating the self-filling capacity of these UHPC-like materials in order to keep the durability, the long-term durability performance that we wanted for our application. Thank you very much for your attention. Welcome any questions.